Hello, everyone. We will give it maybe another 30 seconds just to let people filter in before we do introductions and maybe go over what it is that we're going to chat to you all about today. We're very happy to have you here, and I'm very happy to introduce you to three amazing researchers who work within the field of carbon management. For us to have a nice and sort of friendly discussion around carbon dioxide utilization and carbon dioxide storage, and how that fits into a sort of broader carbon management strategy, and how we sort of think about that for the environment. We thank everyone that sent questions in. We're going to try to get through as many of those as possible, and for as many different types of questions as possible. And yeah, that's kind of where we're at. Maybe now would be a good time, actually. I think there's, a couple of minutes past. So yeah, I will take 10 seconds to introduce myself, and introduce the Global CO2 Initiative. So hi to everybody, I'm Stephen McCord. I'm a researcher here at the University of Michigan. I work as part of the Global CO2 Initiative, where we work predominantly on something we call carbon management, and within that we focus our attention on carbon dioxide utilization. This tends to see us focus on thinking about how we can turn carbon dioxide, which is often seen as a waste, into a whole bunch of different products, whether they be sort of long life durable products like concrete, and sort of building materials, or whether they be what we call short life circular products, things like fuels and chemicals, things that you will probably interact with every day and never really think about how they're made. If we really want to move away from a very sort of fossil heavy reliance, we do need to explore sort of alternatives to that. And sort of tied to this is also the fact that, we have a lot of carbon dioxide that we produce every year, and there's an awful lot of it already in the atmosphere. So when we can't use it, what else can we really do with it? And the best bet really is to try to find some way of locking it back away, storing or sequestering that into permanent or semi-permanent locations is one sort of approach we can take for this, and that can help us sort of address this impending climate crisis that we're facing. So without further ado, I will take a second to briefly introduce the three amazing panelists that we have today. And I will get them to also provide a quick overview of what they do and why it is that they do what they do, because I think that that's very important for you guys to understand, as to why people are here. So I have here with me Shang Zhai, who is an assistant professor at the Department of Mechanical and Aerospace Engineering and the School of Earth Sciences at the Ohio State University. Hongtao Zhong, who is an assistant professor at the Department of Mechanical Engineering in Michigan State University. And Haagsma, who's the director of the Michigan Geological Repository for Research and Education at Western Michigan University. As you can see, everyone's very local to where we are, and that was done on purpose. When Christy and myself were thinking about putting this event together, we wanted to explore the concept of, friendly sporting rivalries, but we all live on the same planet with the same problems to solve. So when it comes down to the serious things, we can put that to one side and sort of work together to solve problems. So yeah, let's maybe start with the order on the screen that I have on my screen. So Hongtao, if you wouldn't mind giving a quick introduction to yourself.
Okay. Hello, everyone. It's great to see you here. My name is Hongtao Zhong, and I'm an assistant professor in mechanical engineering. So my research is about using electrified ways to convert CO2 into something really useful. As Stephen just mentioned, one of the application is actually to, we first learn CO2 as the products from combustion by burning fuels, right? And one of my research areas to think backwards. So how to convert CO2 into fuels, or let's say CO2 to fuel, and conversion. And more recently, I've got into like CO2 carbon capture, and also like other ways of utilizing CO2. Yeah, I would like to discuss with you in this segment. Yeah.
That's awesome. That's a real mixed bag of, as you said, I think it's a really nice way of putting it. We often think of burning fuels to make CO2, and now we're thinking about trying to make CO2 into fuels, and that's we turn that carbon back into an energy carrier, and in that nice circular way, so that we don't have to dig more oil out of the ground, which is a great bonus. Thank you very much. Autumn, would you mind giving a quick introduction?
Sure. Autumn Haagsma. As Stephen said, I'm the director of the Michigan Geological Repository for Research and Education, which is a mouthful, so we say McGree for short. And I'm also the assistant director of the Michigan Geological Survey. Both of those fall under the umbrella of Western Michigan University. So I deal with the subsurface side. A big part of what we do is curate, manage, preserve, and make accessible a large collection of geologic samples. These are used in a variety of research. My specialty is in carbon sequestration. I've been working in that field for 13 plus years now, and dabble in various other fields as well. I was drawn into CCUS as a real interesting research problem, but a research problem that made me feel good at the end of the day, where I got to apply my skills and solve a real life problem that we would hopefully see have an improved impact on my generation and future generations.
It's a really nice set of motivation. Um, Shang, would you mind quickly giving a rundown of who you are and what it is that you're up to too?
Sure. Thanks, Stephen, for leading this. And I'm Shang. I'm assistant professor right now in mechanical engineering. My training was a combination of mechanical engineering and a little bit of materials and chemical engineering study. So I'm very interested to solve this very difficult CO2 problem. But starting from my background, I picked the area of using CO2 to convert industrial waste, such as steel waste into construction materials such as cement replacement. I think this topic can better utilize my expertise to help find a better solution. We're developing a new process to realize the steel slag into cement conversion by lowering the energy costs and also increasing the product quality by having high quality cementitious material as the main product. So that is one major topic of my group. My other topic my group is working on is about hydrogen. It's a little different from today's topic, so I'm not going to introduce too much, but I'm very happy to be here to communicate, discuss with everyone.
That's awesome. No, thank you very much for your time. I think the other thing I can do is maybe just point to the fact that you can see from each of these panels that there's a wide range of things that we can do with carbon dioxide. Sort of mentions we can store it in that subsurface. We can think about storing it in some of those materials that Shang's just been telling us about, some of these cementitious materials, or we can think about fuels, as Hongtao also mentioned. For the benefit of everybody in the audience, I will give you a quick heads up on what I do and on how I fit into this, because I'm not just here to ask questions. My work tends to focus around what we call economic and environmental assessments. And we work a lot with startup companies, with other researchers, sometimes with NGOs and the governments, to help people be able to explore the sort of economic feasibility and environmental potential of new technologies in this emerging carbon management field. It's great if we think that we have a green idea, and it might be that we do, but it's very important that before we start, investing and developing these at a breakneck pace, that we can identify which are maybe some of the barriers to sort of deployment, what might be some of the sort of better choices when we have alternatives that we can look at. There's lots of different things, and really sort of make sure that if we're making claims about something being better for the environment, it really is better for the environment. And if we're making claims that something is affordable, that it is affordable. So really we think about sort of assessing sustainability, which is kind of tricky when we're in a fast-paced, constantly moving sort of world where the target's always changing, but it's a very exciting place to be. And it also brings us into contact with lots of interesting people, like all the people that we have here today. I think before we jump into any specific questions, what might be a good idea for us to think about, sort of thinking the fact that this is a very general audience, is anyone here, up for maybe trying to explain in relatively simple terms, like how, let's say, you utilize carbon in each of your different respective sort of works? Maybe take it one step further than the introduction and give an explanation that maybe a first year college student could follow. sort of how is it that you fix or help solve this carbon problem? Does anyone want to have a go at answering first?
I'll hop in first.
Awesome.
So from the geologic side, a big part of what we're looking for are the right type of geologic formations that have the right conditions, like they're deep enough, the right rock type, have the right properties to permanently store and safely store CO2. But from a utilization perspective, there are other ways to utilize CO2 in the subsurface. One way would be for enhanced oil recovery, where you could use CO2 to help mobilize trapped oil. And a percentage of that CO2 gets trapped and left behind, and then you can recycle it. So it's this whole recycling process where you bring it back up, you separate it out, you re-inject it, and you keep going and keep going. There are also some really exciting newer areas of research utilizing CO2 in other ways. One is like stimulated production of critical minerals or rare earth elements. There's some talk of it also being used to stimulate hydrogen production or for enhanced geothermal energy. So there's a lot of different ways to think about how it can be used in the subsurface.
Yeah. So I mean, as well, I mean that's amazing, Autumn. I think there's two things I'm gonna quickly ask you questions out just as follow-ups. One, you mentioned safety. And this is obviously a big risk whenever we're thinking about doing anything, especially injecting things into the subsurface. We see this a lot in our work. Can you explain to people how we do this safely and what it is that we're looking for when we're trying to find those storage sites that are suitable?
Yeah, great question. So one thing I always like to really hit home is the amount of characterization work we do at a site before any injection would happen. There's a program ran by the EPA it's called Class 6 permitting. It's the underground injection control. They have pretty strict requirements for assessing a site to make sure it's safe for storage. And within that, you have to not just characterize the reservoir, so understand, how thick it is, what's the rock type, what kind of pore volume there is, what are the geomechanical properties, what are the injection limitations? So under what conditions could rocks be fractured or damaged? And then, what are the safe operating conditions for that in the future? But also looking at the confining systems or seals, cap rocks. Those are words usually interchanged. So these are the types of rocks that are making sure that CO2 isn't going to migrate upwards. And the same type of information is needed for those. Detailed modeling, 3D modeling is usually conducted as well. So simulating CO2, different number of wells, volumes, injection rates, a variety of scenarios to really simulate and understand what are the safe practices and limitations for your CO2 projects. But then there's a whole series of monitoring that is also required. So looking at detecting CO2 at the surface, at the groundwater, below the surface, in the cap rock, in the reservoir, so that all along the way, how much CO2, if it's been migrating, where is it migrating to, and having plans in place to respond if CO2 is moving where you don't want it to go. And then another risk to think about too is with any type of subsurface activities and changing a system dynamically, the potential to cause fracturing or induce seismicity. Again, this falls into the characterization phase to understand the limitations of your rocks, but also in the monitoring phase to have things installed to detect if there's any type of changes like that. So all of this program is put together to protect the groundwater and ensure that CO2 doesn't migrate into the groundwater or to the surface.
Okay, so it sounds like that you guys do a lot of work before you even drill a hole, and then there's a lot of monitoring whilst you're storing the CO2, and then also just as importantly, you guys keep an eye on where that CO2 goes and measure it for long after it's sort of stored or put underground too. So yeah, that sounds like an awful lot of challenges. Yeah, like how does the actual sort of monitoring work? Do you guys use sort of special sensors, or is there something else that you can track using seismological tools? Or
Yeah, and it depends on the geology, because not every tool is going to be suitable for the types of rocks at that location. So it really depends on the site. But generally there's tools that can be installed in the subsurface along the wellbores. You can track things like temperature or acoustic signals. You can detect seismicity using geophones. People use repeat 3D seismic, so they'll take a picture essentially of the subsurface before anything happens. They'll take a picture throughout, multiple times throughout, so you get this time lapse of monitoring where that CO2 is going. And then, you know, sensors in the groundwater, sensors at the surface, again, kind of thinking all along the way, all the areas you want to protect and make sure they're safe. Yep.
Yeah, no, I think it's interesting you bring up the groundwater. That's obviously something that here in Michigan we've had issues with pollution in the past. So it's nice to see that this is something that is very much sort of front of mind when we're thinking about storing CO2 underground. By the way, anyone in who's sort of here participating as an audience member, we do encourage participation. I believe that you can add things into the webinar chat. So if there are questions you would like to see answered following up some of these things, please feel free to add them, and we'll try to address those as well as the other questions that we already have from you guys when you've registered. Okay, Shang, do you think you could maybe tell us a little bit more about your sort of reacting CO2 with some of these sort of other wastes to make building materials? I mean, to me, that sounds really interesting because what you're doing is kind of taking two wastes to make a product. Could you maybe go over that a little bit more?
Sure, sure. Happy to. Maybe I can step back a little bit.
Yeah, of
I
course.
mean, firstly, probably most of us are aware that the scale of the CO2 problem is really large. It's a gigaton scale because the emission every year by human activities are 40 or 50 billion tons or gigatons of CO2 every year. Therefore, to mitigate this problem or solve this problem, hopefully, we really need gigaton scale solutions. It's very hard. There are not that many gigaton scale processes or industries under control at this moment. I would say geologic related processes, they are happening at definitely gigaton scale. But the full understanding of it, probably we need to further understanding to basically engineer it to help us mitigate the CO2 problem. And industrial-wise, I mean, fossil energy is a gigaton scale industry. We do get a lot of fossil resources today and use it and convert it ultimately to water and CO2. And there are other almost gigaton scale industry like steel and cement industry. That is one of the motivation I wanted to focus on them because they can be part of the solution. I mean, I don't think one single solution of turning steel slag into cementitious material is going to solve the whole CO2 problem, but I think it's a reasonable contribution if we can successfully scale up this technology. And specifically, there are two different needs from cement and steel industries. In cement industry, well, it is always desirable to supply additional supplementary cementitious material, especially when we have less and less coal combustion processes. So we will have less and less fly ash. Those are very popular supplementary cementitious materials these days. So when we have fewer fly ash, how can we develop additional alternatives to serve as the supplementary cementitious material? That is a need by the cement industry. On the other hand, the steel industry, well, they produce a lot of different slags. Some of them are already well utilized, like blast furnace slag. That one actually is well commercialized to be sold to the cement company already because they have very good properties. What we are dealing with is the not so popular or currently useless slags. Those are the steel slags coming out of steel making process. There are mostly two categories, basic oxygen furnace slag, BOF slag, and also EAF slag. These are the electric arc furnace slag. These slags are not welcomed by people because they have components that will expand once you contact it in water. That expansion clearly is not good for any construction purpose. You don't want the structure to expand gradually over the years. That will be disaster, right? So how do we convert these steel slags so that they can be no longer expanding, so they are more ready to be used as a supplementary cementitious material? That is, I would say, the core problem we are solving, because it can really satisfy the two needs of the two industry. From the steel parts, currently these steel slags are pure waste. They pay other companies to take it away and do landfill. So that's a very big cost to the steel companies, not to mention the potential economic risks to either human beings or plant and animals, right? So there's a strong need to make use of these current wastes. On the other hand, if we can convert these successfully, then the cement industry would be happy to see the alternative source of supplementary cementitious material. So I would say that is the overall need that we are trying to address by having this new process that can have CO2 to play the role of converting a waste into a useful material. So CO2 here is enabling the chemistry that is able to make this happen.
That's amazing. Yeah, and I think that there's a couple of things that I'd like to pop in there. I think the first one for the audience, just in case you aren't familiar with this concept of supplementary cementitious materials, one of the big sort of emission sources on the planet today is the production of cement. This comes like the sort of CO2 released in cement comes from two different places. One is from the fact that we need to heat rock up to a very high temperature, about 800 degrees Celsius. Normally, we do that through burning coal or through burning gas or burning pretty much anything else that we can find. And that produces a lot of CO2. But even in heating this rock up, what we're trying to do is transform it into something that will react and into sort of, into the core concept of cement, the core material within that. And that sees it as essentially, for lack of a better way of putting it in simple terms, boiling the CO2 off the rock. So we get two sources of CO2. And this does then account for a huge chunk of the global CO2 emissions. And we only anticipate seeing an increase in demand for cementitious materials moving forward, which means we will only see a constant increase in terms of the amount of CO2 we produce there. So if we can find alternative ways, like the ones that Shang has mentioned in here, to produce these materials or produce cementitious materials without having to do this process, that's generally seen as something that we might want to explore because it may give us an environmental as well as an economic and ecological advantage. I think the other thing you touched upon there, Shang, as well, is that that gigaton scale. When we think about trying to solve climate challenges and we look at the remaining carbon budget and we look at how much we can emit, how much more CO2 we can emit before we start to hit 1.5 degrees or heading towards 2 degrees Celsius of global warming above sort of pre-industrial averages, we don't have much time, and scaling industry takes quite a bit of time. So we're not always looking for perfect solutions. We're looking for good enough solutions that we can sort of work from. And you really did identify the key challenge. Very few things are at that gigaton scale. And most of those that got there, they had a long time to develop to reach that scale. So when we want to think about how we get there without having that time, it's a real big challenge. So, I think that, trying to find these solutions that take, complementary waste and turn them into a new product is a really exciting, concept to me, because I think anytime you can sort of take -1 and -1 and turn that into +2 rather than -2, that's amazing. I think it's a really interesting start. I see there's a question in the chat. I will come back to that after I've just sort of got Hongtao to give us a little bit of an introduction into making fuels out of CO2, because as you touched upon, we think of CO2 being as the product from burning those fuels. So can you talk to us a little bit about how you close that loop and reverse that cycle?
Yes, so I want to mention that the objective is to convert CO2 into fuels. And when you think about this, right, the first people will think about, big chemical plants. There's lots of pipes, like a very mature technologies to convert CO2 into fuels. But then one question you may ask is that, when you do in a traditional thermalized way, probably you have to use some furnace, or like you have to use combustion to heat everything into a very high temperature. And will that also emit CO2? And the answer is yes, like you will also emit CO2 in order to capture or utilize CO2. So my research tool is more focusing on how to use renewable electricity, or more generally renewable energy, to convert CO2 into fuels, because with that you will have a very clean process that you harvest the energy from solar, from wind, from geothermal, from bio, and then you use that portion of energy to convert that into to convert CO2 into fuels. And I want to comment that Shang is working on large scale problem, very large scale, like a gigaton scale. And I'm more interested in how people can use, they call decentralized energy infrastructure, or distributed energy structure. Distributed energy source to achieve CO2 utilization, right? When you think about this fluctuation, intermittent energy supply from the wind, solar, renewable electricity, it actually brings lots of challenges, because then, for example, the catalyst may not work always, in this fluctuation fashion. So the research I'm doing is we are trying to harvest the energy from the electricity and then convert that into some forms of chemical energy, and we call, for example, low temperature plasmas. So we use that in a modular and small scale way, so that we can do this CO2 conversion into fuels in distributed villages, or like rural communities. And the idea is actually very straightforward, is that if we can use renewable electricity to generate some voltage, and it's actually not about heat, it's about energy that we can directly inject into the chemical bond in CO2. And then we can convert CO2 into individual atoms. And then we can kind of reorganize these atoms with some other ways. With some other like gases, so that we can recombine that into, for example, carbon monoxide. This is already a way of is already a form of fuel. So that's actually the basic principle how we do this. We use renewable electricity and convert the energy from electrons to the atoms of the CO2 molecules. And then by decomposing these atoms, we reorganize it to carbon monoxide and even to methanol and methane, so that you can really convert that into fuels without generating additional CO2s.
Yeah, that's like it's almost like you're talking about a jigsaw puzzle made from atoms. And what we're doing is we're breaking down one puzzle to make a new puzzle. And I think you touched upon it in there, and I think the big thing for people to take away from this is that the CO2 itself isn't the fuel, and what we want out of that is that carbon, and we want that carbon because we want it to be the energy carrier. That carbon itself doesn't provide the energy, that primary electricity that you mentioned, the wind, the solar, that's the energy, and we just want to transform that into something that we can use, either somewhere else or straight away, or in a different form. And when we've done work in the past and we've looked at where might we need to keep hydrocarbon fuels, there are certain applications that we see where that people might not think about, but it's very hard to replace them. So we need this alternative sort of source of carbon. So for us, we identified, and I think that maybe you would agree, Hongtao, that if we think about aviation fuel, and this is a really big area, because the idea of trying to create battery-driven planes is pretty difficult because batteries are very heavy. We've looked at things like hydrogen as a carrier, but then hydrogen is about, when you liquefy it, it's still only about 1/7 as energetically dense as a hydrocarbon. So unless we go to having huge fuel tanks on planes, which brings their own challenges, and space is a premium on planes, it gets very difficult to think about how do we continue long distance flying if we don't want to use fossil fuels. And this is where using that carbon as our energy carrier is very, very interesting as a concept. I think I wanted to just ask you a follow-up question about that sort of rural communities aspect that you mentioned, and that distributed network. So I really think just can you explain a little bit more about how you think this sort of engineering application and solution can really be a benefit for that sort of rural community? Is there a specific type of rural community you're thinking about servicing there? Is it particularly remote, or areas that are detached, or?
Right. So when I mention like rural communities, I'm basically saying that the communities with limited infrastructure, for example, to centralize chemical power plant, like a chemical plants or power plants. We are saying like, okay, in one community that for the energy they are supplied by wind solar, sorry, like a solar panel or like a wind energy. And for this community, people already demonstrate that we can so by converting the voltage harvested from the solar energy, and we can convert this part of energy either into battery to start it, or we have a small scale reactor that we can convert the CO2 emitted by the community into some value-added chemicals like CO and methane. So that's already been demonstrated, and people are interested in this type of technologies that because in many places we don't have large power plants and we don't have any like a centralized facility to process CO2, and then this process will be very helpful for people to convert CO2 into value-added chemicals. Yeah.
That's awesome. Yeah,
Yeah.
thank you.
Yeah.
I am going to just change track quickly, guys,
Yeah.
and look at these questions that are in the chat before I go to the list that were pre-submitted. So Dan, I apologize, I'm totally going to get your name wrong here, but Dan Hamalainen asks, or mentions that he's personally very interested in biochar made at scale as a method for sequestering carbon and improving soil. He asked the panel members, how do you feel about the potential of biochar in their areas of expertise, e.g. burying biochar, including biochar in building materials, etc. So I will quickly try to answer what I see from this, but then we'll also give everyone a chance to weigh in as well. So I think that, Dan, you've touched upon a really interesting sort of solution, and this touches back a little bit across what Shang mentioned before about these gigaton scale solutions. And that's kind of sort of implicit in some of what Autumn was talking about storing the CO2, where really we are trying to store large volumes as fast as possible. So biochar is what we would call an open source, like an open system type solution to carbon dioxide removal, where we might use biomass materials to produce this biochar and then take that trapped carbon and as you mentioned, store it underground or store it somewhere else. I'm very interested and very intrigued by the concept. I'm very excited about the concept of scalability, specifically for things like this, and some of those other open system sort of solutions we see, like the ocean capture and storage, enhanced rock weathering, they have a lot of potential, but they do come with an amount of risk. And that's basically in how do we, make sure that that carbon stays trapped. Biochar has that to an extent. And one of the things that I have personally seen as a sort of particular big challenge when it comes to biochar and one that is being worked on is that, depending on where you store it, there's a fraction that can escape. So when we think about trying to turn this into carbon credits or, try to generate a way of creating value or deriving value from this sort of biochar thing, biochar approaches, there are still some challenges there in that sort of MRV side. But I think that it has a lot of potential in terms of being scalable as a carbon storage sort of method. And I think that we understand how to make biochar very well. This is something we've done for a very long time. One of the areas where we really need to catch up is that sort of scalability in MRV and scalability in terms of being able to ensure that we are actually delivering the carbon reductions we're claiming. Does anyone else want to add anything around biochar?
Yeah, I'm happy to add my thought as well.
Yeah,
I agree. The upper limit of biochar, the scale is very high, right? We can potentially have a lot of biochar made if the process is scalable. So that's a part I personally like it as well. In terms of how we evaluate the scalability, I mean, from my training as an engineer, I usually think of the process cost and energy. So there are many different processes people are inventing or developing that can make biochar. They have all different system design and process analysis. It will be very important, I think, to look at the estimated energy need and how much impact will that energy consumption be when we produce, for example, gigatons of biochar.
Yeah.
That cost and energy would be a important metric, I think, when we evaluate these technologies. Another thing I think, Stephen, you also mentioned about a lifetime. So biochar, I think, is um, it's pretty stable, but there may be a chance of the carbon escaping and coming back into the environment. So that's another thing I think we can, when we deal with a specific technology, we can evaluate and estimate the lifetime of carbon that can be stably sequestered inside the biochar. Yeah, overall, I'm very interested in this biochar idea, and I think there are many different processes that people can work on to improve the figures of merit.
Yeah. Yeah, I think the other thing that, I forgot to touch on in the first place as well is also, when we think about gigaton scale, it's where are we going to get the biomass from? And I kind of think that you touched upon that a little bit and about what does that mean in terms of land use change? And is there risk there? It's okay if we're using biochar from, waste materials or from forest residues or from, other agricultural residues. But is there a risk if we start sort of growing large amounts of biomass specifically to make sort of biochar? Then there are, upstream concerns that we, as in sort of the people that work in my area, would be particularly interested in. And it's a big challenge when we look at land use change, and the environmental impact of land use change is actually pretty difficult to quantify. So yeah, there is a lot of potential, but maybe some risk. Hongtao or Autumn, do you have anything to add? Or shall we move on to the next one? Okay, let's ask about, so the next one we have okay, I can't say anonymous today. Anonymous attendee, that's too many years, that's why. Asking, how do we scale CO2 to fuel? And then they ask, is it a direct air capture system? Because I'm thinking about entropy and the second law of thermodynamics. Hongtao, is there anything that you'd want to sort of address there?
Well, I would say CO2 to fuel is being this topic has been discussed a lot, and people actually tried both direct air capture or, like, for example, you have a point of source for like CO2, for example, at the exit of a power plant where you have a lot of CO2, and then you can do the CO2 to fuel at the exit of the power points. Sorry, like the power plants. So I would say for direct air capture, if you want to use the capture CO2 and convert that into CO, of course, like you are facing the challenge of the low conversion yield and also the high energy cost. That's definitely one challenge we are facing when we talk about CO2 to fuel. Yeah, but at this current step, there are many kind of emergent opportunities actually to overcome this. For example, like by developing like new materials. For example, there's a material called dual functional material is essentially to answer this question. It's like, you have two materials. One is to capture CO2 from the air, and then the second material is to catalyze the CO2 and convert that into methane. So that's actually some people's kind of practice, like people's like solution to solve your question to overcome this challenge. Yes.
Yeah, I think I'd just like to add here as well, that we know that we can't beat the second law of thermodynamics. That's one thing we accept when we try to make these types of chemicals or fuels. What we are trying to do essentially is match need, conversion need to an energy source. So we know that we are not going to, get the same energy out as we put in. And that's okay, because what we try to do is we can prioritize things that don't require conversion. And then we can think about, where do we need to make those products and where do we need to pay that energy penalty? So if we have to go from electricity to hydrogen for electrolysis, and if we have to go from hydrogen mixed with CO2 to, fuels, hydrocarbon fuels or chemicals, and that's okay. We know we have those energy penalties and we know that that does create system level challenge. But sometimes we do just need to pay them in the same way that we have to pay many other things, because if we want to deliver that function, that's the thing. And this is always why we see this challenge between maybe sort of electric vehicles and sort of road fuels. And sort of, when and where does it make sense for us to make those conversions is a big part of the work that we do. And I imagine it's a similar thing for you.
Yeah, so I want to add one thing that because we are using renewable electricity to power this whole process, and the renewable electricity itself is like wasted in the past. So we actually don't use like high like a high quality energy to convert CO2 into fuels. Instead, we use some energy that has been wasted before, and we try to develop technologies that can kind of get used to this like fluctuation, intermittent energy supply to convert into fuel. So that's something you need to consider. Like we are not dealing with the high quality energy from the beginning.
Yeah, that's it. Curtailment is an issue, as you mentioned.
Yeah.
There are times when we have these sort of intermittent supplies that they just don't match up with demand.
Right.
Sometimes it's a case of grid congestion. Sometimes it's a case of various other things. But yeah, there is certainly an amount of curtailment that we can certainly use as well there. Does anyone else want to add anything to that question? Or if not, we have a question lined up for you, Autumn, specifically asked by someone for you. So Ranjit asks, what measures are in place to ensure that injected CO2 does not contaminate groundwater, and how are monitoring tools used to verify long-term isolation?
Really important question. So the most important part is making sure that we have an efficient cap rock. So that we have relatively thick rock that is non-porous, non-permeable, so that CO2 is not going to migrate up through it. And in most cases, you'll have multiple of those layers that are separating where you're injecting and storing CO2 from where your drinking water is. I'll use Michigan as an example because that's what I know best. In Michigan, anything below 1,000 feet gets really salty really fast. So the water is not a viable source for drinking water. All of our drinkable water is less than 1,000 feet or less typically. And you're looking at injection zones at least 2,600 feet or deeper, usually deeper. So you have thousands of feet that are separating from your reservoir and your drinking water. And many of those types of geologic reservoirs should be these types of cap rocks. And that's part of that characterization process. But to ensure that long-term safety, we do have to have these different monitoring techniques to map out and monitor where that CO2 is migrating. So as I mentioned earlier, there's a lot of different types of techniques. There's some really great resources out there if you're interested in diving deeper into those. I would recommend looking at the research that came out of what's called the Regional Carbon Sequestration Partnerships. They're large regions across the United States that did just this, was looking at the different types of technology, testing them out, doing pilot scale injection tests, seeing what technologies are viable and kind of what is really needed to help guide the development of projects. But what comes out of those is that, there's different sensors all along the way. You have to be watching the surface. You'll be monitoring the water. You can use monitoring wells for that with different types of sensors. In those cap rocks, you'll also have monitors for changes in pressure and temperature, because that will indicate if there's any CO2 movement, and in your reservoir too, and you'll have multiple monitoring wells, and then also using geophysical tools too to do a more of a larger scale map, time lapse over time. So depending on where you're at, there are different requirements for how long you have to monitor a project. You certainly have to monitor through the entire lifespan of the project, and then 50 years plus that. In some states, there are different types of requirements where if you can prove that that CO2 hasn't changed over a certain period of time, then you can lower your monitoring requirements for longer term. So I mean that kind of comes into the regulatory policy space, depending again kind of where you're at, what state, what country. They all have different requirements, but it's all designed really to protect the groundwater.
Yeah, so I mean, it sounds like that basically cap rock sits here, CO2 sits here, and then several layers of rock, ideally between that and the groundwater, and then this is something that you guys keep an eye on over time. And I think you mentioned the interesting thing that as more and more states get primacy, we'll see how more and more people want to sort of handle this. But I think that generally what I've seen, and maybe you can sort of confirm, is that there's a lot of caution around how we approach this, particularly because drinking water is such a sensitive thing for most communities.
Yeah, absolutely.
Awesome. Okay, I apologize because I'm totally going to butcher this name. This is my bad. Shigofatso Sheila asks, or says, it was mentioned that a solution is being developed in relation with methane production in rural communities. So Hongtao, I think this is for you. What are the challenges that you guys have seen with scaling? I ask because there is a lot of interest in rural development, especially in the developing world, and I want to understand the constraints and scaling it better.
Yeah, so first of all, thank you for asking this question because I actually have the experience of scaling up with the local community. And the very first challenge we encounter is the cost. So it's like in the lab, like we can use very exotic and novel catalysts, for example, or like power supplies that can have very high efficiency and energy and very low energy cost, as demonstrated in journal papers. But when we come to the community, it's totally different story because like we need to solve the problem of the cost. Like they need many like kilowatt capabilities. And the first question is like, how do you balance between your efficiency or like the effect with respect to the cost? You need to develop some low cost power supplies. That's very important, for example, for electrified technologies. And what we do in the end is that we found like some they call DC-DC converters used to work very well in like high voltage industries. So it's like complete something like new in this community. Like we bring in this, and as a result, we can reduce the cost. For example, for the power supply, we used to spend like 10,000 to buy. Now we use $50 to buy this. But of course, the efficiency drops down, and then you need to customize your system to make sure it can work, so it can function as you expect. So that's the first thing. It's about how to reduce the cost from lab to the to the deployment. And the second thing I want to mention is about the resistance. So when you have this system outside in rural communities, you have lots of like a disturbance, unexpected surprise for you. And I remember at that time, every time we went to the farm to check our facility, and the reason it doesn't work is just very interesting. Say like some animals ran into the device, so things like that. So you need to consider like it must be robust to weather, to all the conditions there. Yeah, so those would be my two experiences with scaling up. Yeah.
I think that's some really good insight, and I think there's one thing I'd like to sort of really like highlight of that is that very engineering solution to a problem where if we're in the lab, we have access to a whole bunch of things that might be prohibitively expensive, especially
Yeah.
as we go outside. And for those of you that are in the audience as students and are sort of thinking about careers in engineering, this is actually one of those big sort of challenges that we all face. That sort of pipeline from ideal clean room conditions down to actual operation, where cows and sheep might run into your equipment and knock it over and break it. There's a big challenge about sort of taking things off paper and putting them into the lab and then taking them out of the lab and into the real world. And I think that's probably one of my favorite bits about sort of being an engineer. It's sort of thinking about how can we take something we found and then turn it into something that's useful for people. And that can be whether we're making chemicals, whether we're making sort of concrete, whether we're making or whether we're trying to store CO2 underground to help us fix our climate issue. All of these come with engineering challenges, and we work on trying to develop solutions to these, and then we have to work out how to deploy them. I just think it's super exciting. I'll try to get through as many of these as I can, but there are so many questions and so little time. Shang, I think this one might be for you. If an anonymous, no, I'm not going to say anonymous again. If concrete offers durable CO2 storage, it's manufactured by concrete plants in every city and is used to create essential infrastructure such as buildings and roadways. Why are DAC solutions so focused on treating CO2 as a waste via geological storage? Maybe this actually touched on that one as well, especially considering the regulatory barriers and geographic limitations of geological wells.
Sure, I'll be happy to start and anyone can chime in. I think we need to clarify here the traditional cement production. Actually, Stephen already mentioned early on. The traditional cement or concrete production has a lot of net CO2 emission because firstly, the limestone calcination releases CO2 from the chemical reaction. of calcium carbonate going into calcium oxide and CO2. So that is the big net CO2 emission from cement production. Additionally, the process requires high temperature heat. Producing the heat traditionally uses combustion of fossil fuel that contributes to almost equally large amount of CO2 emission. So therefore, traditional cement or concrete production has several gigatons of CO2 emission per year globally, I think. And the new cementitious materials people are trying to develop with many different technologies. These are potentially having, including our process, we are targeting to have net zero or net negative CO2 emission for this new type of cementitious material. I mean, these technologies are all in different stages of development. I mean, people are trying to make them large scale, but right now, none of these new type of cement has reached gigaton scale. So hopefully that clarifies the difference between traditional cement and these new cement production pathways that we're looking at. Stephen or any others, please add. If you
Yeah, is there anything you'd like to weigh in? So it touches that sort of geological storage part.
Just going to echo some of the thoughts that Shang had, even earlier in the panel discussion on scalability. When we're looking at where we can make the greatest impact the fastest, that's in subsurface storage because we have the capacity, we have the technology, we understand subsurface management. Going off of a history of oil and gas, waste disposal, brine disposal. We have the type of technology and tools that we need to inject and store CO2 at large scales.
Yeah, I think that I'd go along with that, and I think the other thing that I'd really want to sort of highlight is that this kind of the question presents this as an either or. Really, it's both of an and. Luckily we have so much CO2 and produce so much of it every year that we aren't going to run out of it in terms of trying to store it in materials or trying to store it underground. That's actually our problem. We really have a need to do as much of it as possible in as many different directions as possible. And I think that we mentioned earlier on that this is a gigaton plus scale problem, and we don't have the time to really get there. In terms of the time it took, you can find a whole bunch of. I wish I had the graphic on hand, but there's a whole bunch of graphics that show how long it took certain industries to reach gigaton scale. And, unsurprisingly, we're talking decades in most cases. If we want to limit the amount of global warming, sort of in comparison to pre-industrial levels, we just simply don't have necessarily the time. So I think at the minute, it's all hands on deck and try to solve as many of these as possible in every direction. But yeah, no, thank you very much for a great question. This one's a little bit different. I kind of think it's a nice change of pace. Alec Haupt asks, what partners do you see in industry demonstrations and pilot projects when trying to transition technologies from the lab into the real world? As a carbon capture startup founder, I see lots of people interested, but few or none wanting to put up money for a paid pilot. Does anyone have any thoughts around any of that? No, I can answer. I'll give a rough answer as someone that has worked with startups. I think the biggest challenge tends to be being able to demonstrate that you can do something, whether that be in lab, and then or sort of a very small scale pilot and finding funding for that. And what we tend to find is that as a startup, as someone who's a startup founder, you probably know that there's this weird what we call the valley of death in terms of funding. Where if you're at a very very small scale, you can find funding from some sort of traditional bodies like NSF, who will fund lab scale research. And if you get towards that, that very big high end scale, where we're talking about TRL 8 or 9, which are technology readiness levels, where we're talking about, full scale pilots or mature technologies. You can tend to find mechanisms or financial mechanisms that help you, get funded. Really, that sort of first of a kind pilot and things in the middle is a challenge. It's not a new challenge, but it's a challenge that everyone faces when we're thinking about carbon across different ways of carbon management. In terms of trying to transition from the lab to the real world in that sense and build a first pilot, I think it's sadly a case of persistence and sort of trying to find the right partners at the right time. And you'll find that that's actually the thing. When you've proven that your technology works to an extent, it's very much about sort of perseverance and finding somebody. And sometimes that can, from the companies I've spoken to, that can happen relatively serendipitously. They are, in the right place and meet the right person, and that person can put them in touch with somebody. Or sometimes it comes from being able to demonstrate something in a lab, and they can find, a tech accelerator or something like a funding body. Maybe not ARPA-E, who would be a little bit bigger in terms of scale, but someone like a DOE who has specific pots of money here in the US available for first of a kind pilot scale type things. It's very much sort of very globally dependent. I don't know if anyone wants to add anything beyond that to that question. And Alec, if you would like to chat more about it at some point, feel free to send me an email. I'd love to try to help solve whatever issue it is that you're running into there. But yes, anyone?
Yeah, and also I want to mention one thing is that I think for like carbon capture startups, like one way is to think about like SBIR or CTR opportunities, like not only in DOE but also in ASF and DOD, because like they really encourage small business to partner with either universities or like some like government agencies to demonstrate the capability. For example, they can deliver some products. That's very important because I was in one NSF SBIR projects, and basically we just proposed we can deliver this chemical to the local farmers. Yeah, so that's something that's actually good opportunity for small business. Yeah,
that's some really useful help. So yeah, I hope that helps. Moving on, Jennifer Petoski asks, what do you think about CO2 capture from water? I will add something here, and that says that I've not done too much on CO2 capture from water, direct ocean capture, so I can't really comment much on that. Where I have seen sort of my experience in this area has been more about enhanced alkalinity in oceans, and I mentioned that earlier with these open systems that have potential to be hugely scalable to gigaton. Ocean alkalinity enhancement sees us essentially add alkaline material into the ocean that sort of changes carbonate chemistry, changes the pH, and also pulls carbon dioxide in to react with this carbonate material or with the alkaline material, and that acts as a sink for it reduces ocean acidity and traps carbon dioxide. Now, the big challenge there is A, proving that you're doing this long term, and B, trying to understand how much CO2 you're taking up when compared to the sort of counterfactual, as well as making sure that, to your maximum, as well as also making sure that you understand any risks that come from sort of changing marine biochemistry risks and various other things. There's a lot of research in that space. But CO2 capture from water, I can't add anything about. Does anyone else have anything that they could mention? No, sorry. There are definitely companies that exist out there, and there are some very interesting and exciting ones. And it shows you the breadth of this sort of carbon management space. That you can always find something that that we don't know something about. But maybe trying to answer one last question, because I'm also aware that it's 4 o'clock. So Sarah Parikh asks, what type of government policies are required to accelerate the path of using CO2 as a feedstock? So does anyone have anything that they want to ask or answer as a sort of final answer? I think there are a whole broad range of different things that we can see in this space, from sort of regulatory to voluntary to to push and pull type emissions trading schemes. But Hongtao, Shang, Autumn, anything that you would particularly want to address?
I mean, I'm aware the 45Q tax credit of CO2 utilization or sequestration is like a financial incentive for many technologies. Yeah.
And similar, there could be some, statewide incentives too, or it depends on the scale of the government too, from, a local, state, federal. There's all sorts of different types of policies and incentives.
Yeah. I mean, if you were to ask me to especially on the utilization side. If you were to ask me to design my perfect policy that a state or a government could enact, I would start, asking to see purchasing mandates for public works that see us, ask to use a certain fraction of alternative materials when building roads or bridges. Let's replace 5% of aggregates or 5% of cement in those public works to start with, the type of materials that Shang's working on, for example, where we can sort of take these alternative materials and, help create a demand signal. That can help, smooth out some of those financial risks. And it can really be quite positive. And we've seen steps towards that in California already, and we might see that elsewhere. But yeah, that would be my ideal thing. And a similar sort of thing in terms of if we're thinking about fuels, especially in that sort of utilization space. If we see things like, the European Union discussing wanting to see a set fraction or a minimum fraction of fuel be renewable or be sustainable fuel, that can also help create that demand signal that helps, companies develop these processes and sort of go and gives them that opportunity to grow, because, there's a lot of risk in this space. So knowing there's a market and knowing that there's sort of friendly conditions that are there to help them explore and be competitive is probably where I would see as a reasonable starting point. I know we've now gone 2 minutes over, so in the interest of being sort of respectful of everybody's time, I will stop. But yeah, I more than anything want to thank our wonderful panelists for joining us today, and thank you guys, the audience, for sticking around. I found this to be really interesting, and if anyone in the audience does have any further questions, feel free to reach out to me, and I'm sure the rest of the panelists will also be happy to respond to you guys and talk more about what they do, because a big part of what we do here at university is try to spread information. So thank you very much. Thank you all to the panelists, and thank you to the audience. If there's anything any of you would like to add before we leave, please feel free to do so. And if not, thank you for your time this afternoon.
Thank you for hosting and bringing us all together.
Yeah, thank you for hosting. Yeah.
Anytime. Yeah, I look forward to speaking to you all soon. Thanks, and thanks everybody.
Thank you. Bye.
Bye.